Hello everyone, I am Revan Janjaram from ME Software Engineering. My topic is bin packing problem. Here we will explore different algorithms for solving it and their implementation using C language. Here the bin packing problem is a classic optimization problem in computer science. It involves packaging items of various sizes into bins with fixed capacities, aiming to minimize the number of bins used, and this problem is NP hard, meaning that the number of items grows. Finding the optimal solution becomes computationally challenging. And for the here the problem statement is like, we to get the problem, I mean, we are given a set of items each with a specific size and a bin with a set of capacity, and our goal is to arrange the items in the minimum number of bins without exceeding the capacity of each bin. And this problem has real world significance in fields like logistics, while minimizing the number of containers or trucks is essential. And if we come to here, the applications will be seen here. I mean, the bin packing problem is highly applicable in areas such as cloud computing, where resources are allocated based on demand, load balancing in data centers, and in logistics for effective packaging. It also applies in manufacturing when arranging products for shipment or storage, where space utilization is crucial. And we will come to the types of bin packing algorithm. To solve this problem, uh, we use two main approaches: heuristic algorithms and exact algorithms. Heuristic algorithms like first fit and best fit provide approximate solutions quickly. Exact algorithms such as dynamic programming and branch and bound aim to find the optimal solution, but are often impractical for large instances due to their complexity. We will see the first fit algorithm. The first fit algorithm is a straightforward heuristic method. It places each item in the first available bin that has enough space. If no such bin is found, a new bin is created, and this method is efficient for time but may leave space unused. And if we will consider the first fit algorithm, here we initialize bins and loop through each item and place it in the first bin that can accommodate it. If no bins are available, we open a new bin. Then this approach doesn't always yield the optimal number of bins but works quickly. If we come to the advantages, it is fast and simple, and disadvantages is most of the space will be not used, I mean unused. Here we can see the first fit first fit algorithm code in C, and we initialize an array to store bin capacities and iterate over each item. The item is placed in the first available bin, and if none is available, we create a new bin. This code structure is similar across most heuristic algorithms, with variation in how bins are chosen. And here we consider the best fit algorithm, and here we place each item in the bin with the least leftover space. And coming to the algorithm, this approach minimizes wasted space but takes more time, as it involves searching for the best bin for each item. The code is similar to first fit algorithm, but requires tracking the bin with the smallest remaining capacity that can still hold the item. For the worst fit algorithm, uh, it is just opposite to the best fit algorithm. It places items in the bin with the most remaining space, keeping larger bins available for future items. While this method can prevent early fragmentation, and it can sometimes lead to suboptimal packaging. And if we come to the algorithm, for each item we need to find the bin with the largest available space and place the item in that bin. Here if you observe that the advantages are, it reduces large unused space quickly, and disadvantages are it can lead to suboptimal bin usage. And if we come to the code, Here it is same as the above codes, but here the code iterates to bins to find the one with the largest remaining capacity. And the next algorithm is next fit algorithm. The next fit algorithm sequentially places items in the current bin. If an item doesn't fit, it moves to a new bin. This gives a simplest approach requiring less computation, but it doesn't consider bin utilization, often leading to more bins. And if you consider the advantages, here it is fast and with linear complexity, and the disadvantages are often less space efficient. Here if you observe the code, it will be similar to the earlier algorithms. Here we will, we will place the items in the current bin, and if an item doesn't fit it, it will move to a new bin. And exact here there are some exact solution methods, and in those are of three types: dynamic programming, branch and bound, integer linear programming. These aim for the optimal solution. Dynamic programming stores intermediate results to avoid redundant calculations. Branch and bound uses a tree structure to explore possibilities while pruning unpromising paths. Integer linear programming formulates the problem into mathematical equations for optimization. Although these methods provide optimal results, they are computationally intensive and mostly suited for smaller instances. Here it gives the comparison of all algorithms. First fit is fast but may waste space. Best fit reduces wasted space but takes longer due to extra checks. Worst fit keeps bins available for larger items but can cause fragmentation, while next fit is very simple but less efficient. Choosing the best algorithm depends on the application requirements such as time constraints versus space efficiency. Yeah, here to provide the code summary, the code for each heuristic they share a common structure but differ in how they select bins. First fit and next fit are simple in logic, while best fit and worst fit involve additional checks for optimal placement within each bin. And the key differences will be: first fit is quick but may leave empty spaces. Best fit searches for optimal placement taking more time. Each algorithm is adapted depending on the priority of speed versus space efficiency. And if you consider this some sample input and output, this illustrates that how best fit can sometimes achieve fewer bins but may require more computational steps to find the best placement. And here we will consider the performance comparison and heuristic performance. Here most heuristic algorithms have a time complexity of n cross m, where n is the number of items and m is the number of bins. Next fit is faster with O of n but less optimal. While heuristic solutions are quick, exact algorithms deliver optimal solutions with higher computation costs, making them best for small scale or high priority tasks. And here this gives us the applications in real life. Each algorithm has its own practical application, and first fit is great for application where quick approximate solutions are acceptable, like online scheduling. Best fit is well suited for memory and storage management where space utilization matters. Worst fit is helpful in manufacturing where keeping large spaces available can be advantageous. Next fit is often used in sequential packaging tasks like assembly lines or conveyor systems. And these diverse applications highlight the flexibility of the bin packing problem and its algorithm. And the conclusion. To conclude, heuristic methods provide efficient, quick solutions, especially for large-scale applications where approximate solutions are acceptable. Exact algorithms ensure the minimum number of bins but at a high computational cost, Overall, the algorithm choice depends on specific requirements such as speed versus optimality. Understanding these algorithms allows us to apply them effectively in real world scenarios, maximizing efficiency and resource uses. And coming to the final thought, the bin packaging problem illustrates the trade-off between efficiency and optimality with wide-reaching applications in logistics, computing, and manufacturing. Thank you.